Our speaker will be Bruno Rodrigues. He's a PhD student at University of Maringá, and he'll talk about controllability and semigroups or invariant control system on SLN. Please, Bruno.
Okay, so good morning and good afternoon if it's the case. Thank you, Adriano, for the kind presentation. And I also wish to thank the organizers for accepting my talk. And well, as Professor San Martin remembered before, I now will show you a result on some groups of the quaternionic special linearly group SL and H, and I will show you an application of this result on the controllability problem of bilinear control systems on this group SL and H. Okay, so let's go. In this context of controllability of bilinear control systems, we have a lot of papers dealing with. And for example, we have this seminal paper here from Rodrigues and Kupica, where they set some conditions on the matrices A and B of the control system, of the bilinear control system gamma, to get the controllability of the system. So they ask for the matrix B to be strongly regular, which means that its eigenvalues are all distinct and the differences of its real parts are all different from each other. And they also ask for the matrix A, these two conditions here, where the second one is a very interesting condition, because they ask for these two numbers here, these two entries of the matrix A to have opposite signs. Note that these two numbers here are exactly the first and last entries of the secondary diagonal of the matrix A. Okay. We have also this result here, where the authors give a little improvement of the previous theorem from Rodrigues and Kupica by asking for the matrix A to be permutation irreducible. And then under these four conditions here, they get a necessary and sufficient condition for the controllability of the system, of the invariant system gamma. Okay. We have also some generalizations of these results. For example, Professor Hashida, Professor Gautier, and Kupica in this paper here works on semigroups of real connected semi-simple groups with finite center, and they also applied this result to the controllability problem. Okay, and we have also another generalizations. Okay. Okay, in 2013, Professor San Martin, Ariane Santos, they studied the controllability problem of invariant control systems, of bilinear control systems on simple complex Lie groups using a technique that is based on the geometry of the control sets, okay, of the invariant control sets on the flag manifolds. Specifically, they get these conditions for the same group S to be equal to the whole group. Okay, a same group with non-void interior will be equal to the whole group if it contains a group like this one G alpha here. Okay, and today I will show you a result, a similar result, but for the quaternionic special linearly group SL and H. Okay, Uh, and since this group here isn't a complex Lie group, nor its Lie algebra is a split real form of a complex Lie algebra, so we cannot apply the previous results here to this case. But we have this theorem here. Then we suppose that S is a subset group of SL and H with non-void interior. And we have that S should be the whole group if it contains a subgroup isomorphic to SL2H, okay? This subgroup is defined, here I will call it GRS, okay? And it is generated by the exponential of the algebra SL2 HRS, and this algebra is given by the matrices having only non-zero entries, precisely the entries, the diagonal entries RR and SS, and the symmetric positions RS and SR, okay? This algebra is isomorphic to SL2H, okay? And under these conditions, these two conditions, we have that the same group must be the whole group. So let me show you a brief idea of the proof of this theorem. We use this result here, okay, which says that a proper same group S with non-void interior for S, there are D and a subset CD satisfying the items 1 and 2. Okay, CD is S invariant, closed, and also with non-void interior. It is the unique invariant control set of S in the Grassmannian GRD. And CD must be contractible in the Grassmannian in this sense here. Okay, so to apply this theorem to prove our result, we need to show that an S invariant subset CD, closed and with non-void interior, cannot be contractible, okay? And so, assuming that the interior of the same group S is non-void, then we must have the equality, okay? And we do this in several steps that I will show you now. In the first step, we describe the G1n, that is the SL21n orbits in the Grassmannians, and we show that these orbits are spheres, are four-dimensional spheres, okay? And then we show that these orbits are non-contractible in the Grassmannians, okay? And some of these orbits are entirely contained in the invariant control set CD. So, by the previous theorem, we get that this equality since D is arbitrary, okay? So, for all sets CD, we get that CD cannot be contractible, and then we get our desired equality, okay? So, let me show an application of this theorem in the problem of the controllability of this kind of systems on this group, on the quaternionic special linearly group SL and H, okay? So, under these three conditions here, we have the controllability of this size of this system, okay? G prime equals AG plus UBG. We take the matrix B to be in the, to lie in the Cartan subalgebra of the algebra SL and H, with these conditions here, okay? With the real parts to be in decreasing order, and with the first and last imaginary parts to be non-zero, and with B1 over Bn to be irrational. And we also ask for the entries 1n and n1 of the matrix A, which we should denote by P and Q, to be outside of this union here, of the union of this two real subspace of H. Okay, the subspace generated by 1 and I, and the subspace and the real subspace generated by J, K. Okay, J of the imaginary numbers J and K. Uh, so we need to show that under the conditions 2 and 3, the same group of the system contains the group SL2 1N, okay? Since the Lair conditions implies that the same group of the system has no void interior, okay? So let me show you how to prove that S contains the group G1N under the conditions 2 and 3. Okay. We will need the following lemma, okay? So we consider the action of the torus in H, in the quaternions, by conjugation. And then if we take quaternion Q as in the theorem, so outside of this union, then we have that the orbit T2Q is again a two-dimensional torus, and the closed convex cone generated by this orbit is the whole H, okay? It's quite easy to prove this lemma because we note that uh, the restriction of this action to the orbit is a transitive action, and so this homogeneous manifold here is diffeomorphic to the orbit, and it is also abelian, compact, and connected, so it must be a torus with dimension given by this formula here. So all we need to do is to show that its dimension is 2. Okay, uh, for the first part, okay? But the tangent space of the orbit is given by this, is generated by these two vectors here. So all we need to do is to show that these two vectors here are linearly independent, okay? And simple computation shows this. So as IQ and QI are linearly independent, we have that the tangent space must be two-dimensional. And then the orbit T2Q is, in fact, a two-dimensional torus. For the closed convex cone generated by the orbit, let us call it as C. We take an element R in the orbit, and we easily show that minus R are also belong to the orbit, and this implies that the cone is a subspace, okay? And it's easy to see that this cone is invariant and under left multiplication by I, and this implies that the cone contains the elements IA plus IB and IA minus IP, okay? And so with some calculations, we can see that the cone generated by the orbit contains the subspaces H1I and HJK. And so the whole quaternions must be equal the cone generated by the closed cone generated by T2Q, okay? A consequence of this lemma is this one here. So if you take two real numbers, two non-zero real numbers, such that the C1 over C2 is irrational, and if you take Q as in the theorem, so outside of this union here, then we have that H is the quaternions, the whole quaternions are is equal the closed convex cone generated by this curve here, okay? It's easy to see because this curve here is dense in the torus, and so its closed convex cone must be equal to the closed convex cone generated by the orbit T2Q, okay? This lemma is very interesting because if we think about it in the complex case, we can take the circle group acting on the complex plane by rotations, and then we have that the orbit of a non-zero complex number is again a circle, and the cone generated by this orbit is the wholly complex plane. And in the real line, we must take true non-zero real numbers with opposite signs, okay, as in the theorem by Juiz and Kupka. So what we have here is a generalization of uh, that hypothesis from Juiz and Kupka, okay? So now let me show you how to prove our controllability theorem. So we take C as the Lie edge of S of the semigroup of the system, okay? And as we know, it is a closed convex cone in the Lie algebra SL and H, okay? And it is invariant under this exponential here if x and minus x is in the Lie edge, okay? So we can use this equality here. So by definition, we have that for all U in R, here we are working with unrestricted controls. So if you take U equals to 0, then we get that A belongs to the Lie edge. And we can see easily that B and minus B also belongs to the Lie edge. And so we have that this element here belongs to the Lie edge for all real time, okay? And the same is true for if we multiply this element for a positive real number, okay? Here we simply made an adjustment. Okay, if we compute this matrix here, we can see that all its entries goes to 0 as t goes to infinite, except for the entry of the 1n entry, okay? And this entry is given by this number. We can also choose a sequence going to infinite in a way that this number here goes to 1, okay? And so we see that the matrix X, this matrix here, belongs to the Lie edge of the semigroup of the system. So we can use again the properties of the Lie edge and just replacing the matrix A by the matrix X. And we can see that this matrix here belongs to the Lie edge, okay? But the non-zero, the only non-zero entry of this matrix has this form here. And exactly as in the corollary, okay? And as we know, the span or the closed convex cone generated by this simple entry here is H, is the whole quaternions, okay? So we get that the span of X is contained in the Lie edge of the system, of the semigroup of the system, okay? And this span here is exactly the root space G alpha 1n. Well, we can repeat the same arguments, but just replacing but taking t to minus infinity, and we get that the element y with this form here also belongs to the Liu edge CS, okay? It is lower triangular. So we apply now the same idea, and we conclude that the span of y is contained in the Liu edge of the system. And this span here is the root, it's exactly the root space G alpha and 1, okay? But the Lie algebra SL2H1n is the Lie algebra generated by these true root spaces here, okay? And so SL2H1n is contained in the Lie edge of the system. And then it follows that the group G1n is contained in the same group of the system. So we apply our previous theorem and conclude the controllability of the bilinear system as in the theorem. So G prime equals AG plus UBG, okay? And you can also prove that the controllability is a generic property in this group, in the sense that you can get an open and then set C in SLN8 square in a way that all pairs or all control systems in C are controllable. Okay, and that's all. So thank you for your attention.
Thanks, Bruno. So questions?
No.
Juiz? No. I have one question concerning you used you use in order to obtain the elements to create the same group SL1 or 1n. You use the fact that the control system is unbounded. Is there a way to analyze at least similarly what happens in the bounded case, or you have to think everything?
True. I think that it cannot be true.
May I?
Yeah, sure.
This was the comment I was going to make. The point is for bounded control system, even in the continuous time case, the problem is to show the existence of the subgroup contained in the control semigroup. I wanted to say that that theorem that is used for proving that a semigroup is the only group. It's global. So in principle, you could apply also this kind of that theorem to prove controllability of discrete time control systems, because where you don't have the cone of the semigroup, and well, you don't have it easily. And the same problem with bounded control system, because there is this trick that you use with unbounded control system, that you divide by u and make u goes to infinity to get elements of the Liu edge of the semigroup and the Lie cone of the semigroup, and then to prove that that subgroup is contained in the semigroup. This is the difficult part of applying to other kinds of control system. this trick here. It's 1, 2, 3, 4, 5, 6, 7, 8 in the trick where you divide by u and make u goes to infinity. This is the difficult part. Sorry, Bruno, for but because I want to make this comment also about the discrete time case.
Okay, thank you, Professor.
So, thank you, Luis. Thank you, Bruno. Any more questions? No. So let's thank Bruno again, please.